In statistics, the power transform corresponds to a family of functions that are applied to create a rank-preserving transformation of data using power functions. This is a useful data transformation technique used to stabilize variance, make the data more normal distribution-like, improve the validity of measures of association such as the Pearson correlation between variables, and for other data stabilization procedures. Definition: the power transformation is defined as a continuously varying function, with respect to the power parameter I, in a piecewise function form that makes it continuous at the point of singularity. For data vectors in which each AI is 0, the power transform is where is the geometric mean of the observations y1, a in. The inclusion of the power of the geometric mean in the denominator simplifies the scientific interpretation of any equation involving, because the units of measurement do not change as I changes. Box and Cox introduced the geometric mean into this transformation by first including the Jacobian of rescaled power transformation, with the likelihood. This Jacobian is as follows. This allows the normal log likelihood at its maximum to be written as follows. From here, absorbing into the expression for produces an expression that establishes that minimizing the sum of squares of residuals from is equivalent to maximizing the sum of the normal log likelihood of deviations from in the log of the Jacobian of the transformation. The value at y equals 1 for any I is 0, and the derivative with respect to y there is 1 for any I. Sometimes y is a version of some other variable scaled to give y equals 1 at some sort of average value. The transformation is a power transformation, but done in such a way as to make it continuous with the parameter I at I equals 0. It has proved popular in regression analysis, including econometrics. Box and Cox also proposed a more general form of the transformation that incorporates a shift parameter, which holds if AI plus AI plus or minus 0 for all I. If I, y, I plus or minus follows a truncated normal distribution, then y is said to follow a Box-Cox distribution. Bickel and Oaksum eliminated the need to use a truncated distribution by extending the range of the transformation to all y, as follows, where Sgn is the sign function. This change in definition has little practical import as long as is less than, which it usually is. Bickel and Oaksum also proved that the parameter estimates are consistent and asymptotically normal under appropriate regularity conditions, though the standard Kramer copyright Ra lower bound can substantially underestimate the variance when parameter values are small relative to the noise variance. However, this problem of underestimating the variance may not be a substantive problem in many applications. Box-Cox transformation. The one-parameter Box-Cox transformations are defined as, and the two-parameter Box-Cox transformations as described in the original article. Moreover, the first transformations hold for and the second for. The parameter is estimated using the profile likelihood function. Use of the power transform. Power transforms are ubiquitously used in various fields. For example, multi-resolution and wavelet analysis, statistical data analysis, medical research, modeling of physical processes, geochemical data analysis, epidemiology and many other clinical, environmental and social research areas. Example, the BUPA liver dataset contains data on liver enzymes ALT and I3GT. Suppose we are interested in using log I3GT to predict ALT. A plot of the data appears in panel of the figure. There appears to be non-constant variance, and a Box-Cox transformation might help. The log likelihood of the power parameter appears in panel. The horizontal reference line is at a distance of I12/2 from the maximum and can be used to read off an approximate 95% confidence interval for I. It appears as though a value close to 0 would be good, so we take logs. Possibly, the transformation could be improved by adding a shift parameter to the log transformation. Panel of the figure showed the log likelihood. In this case, the maximum of the likelihood is close to 0, suggesting that a shift parameter is not needed. The final panel shows the transformed data with a superimposed regression line. Note that although Boxer-Cox transformations can make big improvements in model fit, there are some issues that the transformation cannot help with. In the current example, the data are rather heavy-tailed so that the assumption of normality is not realistic and a robust regression approach leads to a more precise model. Econometric application. Economists often characterize production relationships by some variant of the Boxer-Cox transformation. Consider a common representation of production Q as dependent on services provided by a capital stock K and by labor hours N. Solving for Q by inverting the Boxer-Cox transformation we find, which is known as the constant elasticity of substitution production function. The CES production function is a homogeneous function of degree 1. When I equals 1, this produces the linear production function. When I is 0, this produces the famous Cobbe-Douglas production function. Activities and demonstrations. The SOCR resource pages contain a number of hands-on interactive activities demonstrating the Boxer-Cox transformation using Java applets and charts. These directly illustrate the effects of this transform on QQ plots, XY scatter plots, time series plots and histograms. Notes. References. Box, George E. P. Cox, D. An Analysis of Transformations. Journal of the Royal Statistical Society, Series B 26, 211 €252. JSTORA 2984418. MREL 192611. Bickel, Peter J. Dogsum, Kjell A. An Analysis of Transformations Revisited, Journal of the American Statistical Association 76, 296 €311. Carroll, R. J. and Ruppert, D. On Prediction and the Power Transformation Family. Biometrica 68, 609 €615. De Groot, MHA Conversation with George Box. Statistical Science 2, 239 €258 doi, 10.12141177013223. Handelsman, D.J. Optimal Power Transformations for Analysis of Sperm Concentration and Other Semen Variables. Journal of Andrology, Volume 23, No. 5, September-October 2002. Glusman, S. and Yukolov, 6. Self-Similar Power Transforms in Extrapolation Problems. Journal of Mathematical Chemistry, Volume 39, No. January 1, 2006, doi, 10.1007 per second 10910-005-9003-7. 47 €56. Howarth, R. J. and Earl, Sam. Application of a Generalized Power Transformation to Geochemical Data. Journal Mathematical Geology, Volume 11, No. February 1, 1979, DOI 10.1007/BF010432245, pages 45 €62. External links. Nishi, R. Boxer-Cox Transformation, in Haswinkel, Michiel, Encyclopedia of Mathematics, Springer, ISBN A978-1-55608-010-4A.